Okay, so welcome to Warsaw, first of all. I spent here quite a chunk of my so far, so we say best years of my life, long ago. And so it's nice to be here. And I will be, we will have these a series of lectures, and so we organize them in such a way that sort of we start from like basic tools of celestial holography, and then we package it together with the, so that you will see the purpose of that, so that you see the whole picture, including all details. And lectures are intended to be very elementary. So they will be on Blackboard, and some of us, at least, will be distributing notes, handwritten notes, okay? And now, since it is a school, so of course, questions are welcome. They're more than welcome. There are no stupid questions. They're only, as they say, as Feynman used to say, they're only stupid answers. Okay, so please ask questions, because in this way, you help not only yourself, but you help others, because then it forces the lecturer to repeat and explain a different way, which helps everybody. Okay? So you can interrupt any time. And as I mentioned, it's very elementary level. So essentially, my course will be about amplitudes, but I won't be teaching you how to compute like 5-loop Feynman diagrams. Okay? The idea is to present this whole field of amplitudes, some basic tools and so on, in such a way that it fits into celestial, the program of celestial holography. Okay? So it will be really very elementary, and essentially today, essentially establish notation and explain a few things, and we'll see where it goes. Okay? Okay, perfect. All right, so the first thing, it is a physics course. So it is, I have to talk about units and conventions. Okay, first of all, C equal h bar, and permittivity constant as set to 1. So whenever, for example, you see expression like that, it's like fine structure constant, what it really means is that. Yes? Okay? Similarly, if somebody computes a lifetime, and it comes to be 1 over m, yes? Then you multiply by c squared and multiply by h bar, and then you can have it, then you can compare with experimental data. All right? So that's very important. So that's, as you said, that we are using this so-called natural units for quantum field theory. Now, as far as I'm concerned, here's a tricky part. As far as I'm concerned, I'll use the West Coast metric, which is the signature, which has 3 minuses and 1 plus. I guess I'm afraid it's only in this lecture, so that we'll be facing here. There are many things which there is no way that we coordinate all of us, our conventions. Okay, so I am elementary particle physicist, to say it proudly. So we are using the West Coast metric from Bjerkan and Drell, which is plus, minus, minus, minus. Yes? While those who have background in gravity will be obviously using the opposite signature. Yes? I don't know what Sabrina will be using. Opposite?
Yeah, of course.
Of course, yeah, I know. Yeah, I was expecting, okay, I was expecting that. Okay, so that is the first thing. Okay, now, then what I will be doing, I'll be using some vectors, and I'll be using this kind of contravariant notation. Okay, like positions and momenta, and space momentum. And under Lorentz transformations, that will be the first thing which I will discuss, is Lorentz transformations, which are very important in the context of celestial holography. They set up then something which is like really ground for conformal field theory. So under Lorentz transformation, normally what you do, the coordinates of a given event transform with the Lorentz matrix, And so, which is generated, these Lorentz transformations are generated by boosts and rotations. So, for example, boost in the x direction will have okay, the corresponding, okay, you will lower indices, and it will be some parameter beta, and this betas, it's essentially something which is called rapidity parameters, which related to the speed of motion, and yes.
Minus omega 0, 1.
Omega 0, yes. Oh, very good. Otherwise it will be 0, yes, that's true. Okay. Okay, and what we will be doing, we'll be organizing, it's very convenient to organize these 6 parameters of Lorentz transformation into the complex 3-component vectors, which will have rapidities as a real part, and then the rotation angles as the imaginary part. Okay, this is, of course, well, this is omega 1, like rotation along, let's, for example, along z rotation, will have omega 1, 2, omega 2, 1, and sometimes we'll call it just angle rotation, or sometimes we'll call it like omega 3. Okay, so these are the parameters which will enter into this 3-component vector, which contains all 6 parameters of Lorentz transformations. Okay, so that's the basic thing, and we'll be using it later. Okay, so here we go. The thing which plays the objects, mathematical objects that play a very important role in amplitudes and in celestial holography are spinors and momentum spinors, and this 2-component notation, which the so-called the chiral spinors, left and the right spinors, and they are that's a sort of a basic tool that we'll be using, and this is called the base of so-called holistic formalism and the fields of amplitudes, which allowed making huge progress, and I will explain it later why. Okay, so the second thing is spinors and SL2C group, Lorentz group represented as SL2C. So we have so let's start from Dirac spinors. So they are normally they are 4-component spinors. Okay, which we group into the 2-component left spinors and right component spinors at the bottom. Okay, and then Dirac equation, as you know, will be is usually written like that, and with the gamma matrices, which is very convenient to parameterize in terms of Pauli matrices. It's called Bailey representation, where sigma mu is by convention, it has identity matrix, and then 3 Paulis, and sigma bars have the same thing, but now negative of Paulis as the last 3 components. Okay. This notation actually is what the notation that I'll be using is something which is called Besbagger notation, which is used when discussing supersymmetry. Now, okay, the Dirac equation is a phenomenal equation. It's a really crucial property that is Lorentz invariant. Okay, so this. The theory that they are discussing is Lorentz invariant, and Lorentz invariance, of course, is a symmetry. But what is for us, what is most important feature of any symmetry actually is if equations which are symmetric under some transformations then they are easy to solve because you can go to some special reference frame and boost the solutions to another frame. This is provided that you know how the fields transform. Okay? So what is very important always, you have to know what are the transformation properties of fields, because then from solutions in one frame, which is usually chosen to be the frame in which particle is moving in some simple like z direction, from that you can generate solutions in another frame. Okay, so but for that you need to know the transformation properties of fields. For example, suppose that you have an equation like that, for a vector field, okay? And so if that it's obviously a Lorentz invariant, then okay, we know that if you, the Lorentz invariance means that if you go to a moving frame in which the coordinates of the same event will be rotated by Lorentz transformation, then the new field will have the coordinates which will be rotated by the matrix of Lorentz transformations. Jest za głośno, czy za cicho?
Nie, trochę tak.
Aha, okay, dobra. Okay, so for example, you have like this equation that you have. So if you have an equation, we write the equation d dx prime a prime. Yes, same equation. Then you see that if you go to then the transform field will satisfy it as well. Yes. The equation, of course, what I'm talking is d mu x mu equals 0. All right? So that is a very important thing, and that allows actually, as you will see, you've seen the Dirac equation solved, I'm sure, in course of quantum field theory, but the basic way to, the simplest way to solve it is to solve it in one frame and transform solutions to the other frame. Okay, so for that, of course, you have to know how the, what do you say?
So when we include the Lorentz transformation of the vector field, shouldn't the argument of the vector field also transform?
Could you repeat?
Okay.
You have this A of X here.
A of X?
No, I mean, you have the original argument in the Lorentz transform case. Shouldn't there be also Lorentz transformation of the argument?
Yes, of course, because it is the same place. Yeah,
Okay.
all right, okay. This is something you have to just, yeah, okay. So you have one event, yes? And now it has coordinate x. Now go to a new frame. The same point has coordinate lambda x. You agree with that, yes? All right. Now, in this new frame, you also have a new frame, so it's a rotated frame. So the field, the same field would have the same field at the same point in space-time with coordinates rotated by lambda. Okay, so many other ways. For example, if you see in books, sometimes it's written like that.
Yeah, okay. That was just notation.
Yeah, it's not. Yeah, well, no, I think it's what is. It's important that what you are doing here, you have fields and points which are objects, yes, events which are objects, and now they have different coordinates. That's one way of thinking about symmetry transformations. Yeah.
No, I get it. I just
Yeah.
wanted to,
Yeah, I know. Yeah. All right, cool. All right, so here we go here we go with Dirac spinors. So the one thing which you have seen, and I remember wondering always how Dirac got it. Well, I think he got it not in a direct way. That the components of the transformed fermions transform in the following way: that the fermion component is transformed in the following way. they're rotated by this matrix, which has this rather obscure form. You see, like, say, for example, in the book of Bjarkan and Dreher, and the book of Peskin and Schroeder. So it's 1/2, or I, yes, I have omega mu nu, sigma mu nu. Okay, where sigma mu nu, okay, that's known. These are the related to the commutators of gamma matrices. And then good luck if you want to show that this equation is one around the symmetries. Okay, I'm sure you did this exercise one time in the school, yes? All right. Now, however, what is very important for us, that actually, if you look at these transformations, when you use the Weyl representation and use how separate the left and right components of the Dirac spinors, find the left component, transform in the following way. Now I'll use this vector which I used before. Okay, and this is like a regular scalar product. Okay, and then the right-handed transform separately. So actually, that tells you that Dirac spinor is a reducible representation of the Lorentz group. Okay, and the transformation is like this. You put here psi star, and then times. Okay, so it's perfectly okay from the point of view of Lorentz transformation to transform. So the left transform into left and right into right. Okay, all right. Then the way it's called left and right will become later on when we talk about helicities. Okay. All right. So here, so this is. So now we can essentially. We will not be using this. We will be using just. We can forget about that. Until forever. And talk about separate Lorentz transformations of left and the right components of the Dirac spinors. Okay? So now, and you see actually, now we can call this matrix M. It's, after all, it's a 2x2 matrix, yes? And just by using the properties of Pauli matrices, you see that the determinant of this matrix is equal to 1. All right? So from that, so in fact, what we did here, we started from these parameters of Lorentz transformations, which is this anti-symmetric matrix, and then we replaced that by this, now we replace it. Gee, the chalk here is very fragile for my hand. What do you say?
Because isn't that these generators have trace equal to 0 and not determinant equal to 1?
Determinant of M is equal 1.
No, not of exponent of.
It follows from the properties of Pauli matrices. Okay, that's an exercise. Okay, one thing I should mention, that most of these, big chunk of my lecture is based on lectures which actually I gave here like 5 years ago, which are in physics reports. It's called a course in amplitudes. Okay, so lots of notation is there. The thing which will be different is that I will make a connection, I will rephrase it in a language which is appropriate for celestial holography. So that will be something which will be and that will happen very soon. Okay? So it is that type of the groups. So essentially, this group, this matrix, contains 6 parameters. So a 6-parameter group of complex 2x2 matrices. With determinant 1, this group is SL2C, called SL2C. S is for determinant 1.
Exponent has determinant equal to 1, and the argument of exponent has trace equal to 0.
Yeah, 0, yeah.
Yes, so, and on the board it's like this M.
Okay, all right, thank you. Okay, that's what you meant, yes. Okay. All right. Very good. So in other words, we have now replaced these parameters of Lorentz transformation by this vector then, and then we're essentially replacing the Lorentz rotation matrix, and it will be, or you will see that it will be done for good. We replace it by these SL2 C matrices of SL2 C matrices. So essentially, a Lorentz group is in quotation mark the same thing. I won't go into the SL2C roughly. Okay, I want to make it more precise, but it looks like we are able to perform all Lorentz transformations by using the 2x2 matrices with determinant 1. Okay, so now, so we see how they transform now. Okay. Okay, so psi left is rotated by this matrix, Then the psi right doesn't transform and just by itself, but if you do the following thing, you multiply by 2x2 anti-symmetric symbol, epsilon, okay, then that will transform in the conjugate representation, yes, of SL2C. So this is like in defining or fundamental representation of SL2C, while the right-handed guys transformed under this is like a 2, and this is 2 bar. Okay? So that's what we have. So then what we do, and this sets up the notation, what we do usually now, instead of Dirac spinors, we take the upper component, which I call left-handed, call it spinor with undotted indices, chi alpha, okay? And the lower ones with upper indices, okay? And we can also the lower, and that what we, as you may be familiar with, we lowering and raising indices with this 2x2 anti-symmetric tensor. So for example, eta alpha, okay, we lower in this by using, for the moment, okay, I'll use eta alpha, beta, beta. Okay, I will define precisely which are ones and which are -1 in a moment. So, as I said, chi under Lorentz transformation, the left-handed transform with this by this matrix, and then if you look what happens with look at these guys with upper indices, they transform with Hermitian conjugate inverse. Hermitian inverse symmetric sample. Yeah. All right. So this is my convention. I'm afraid that this convention, okay, this two-component notation, which I'm introducing, appears in an even more striking way in twistor theory, and hopefully that there'll be some connection. There will be some, I don't think, are you using dotted and undotted? Yeah, sure, okay. Okay, but it could be what is meant by dotted and what is my left could be different than what I'm using. So something you say here left was right, yeah, and dotted will become undotted. Some object will become complex conjugate object, but the basic framework is set up here. That's what we do. So for example, if I take, suppose that I do boost and rotation in the third direction. So then I have, so this vector is just has like that and has rapidity boost in the third direction and some rotation. Then this explicit form of this matrix is like that. Okay, so then you see then you see explicit how they transform. All right. Okay, so let me go back to this thing about raising and lowering indices. And so, for example, we started from the undotted spinors with lower index, and then you can raise them, as I mentioned before, with this epsilon symbol, 2 by 2 antisymmetric. And the same thing we already did for the dotted spinors. And then the convention, which I'm using here, it's okay, at some point, may use at some point. This is +1, and the lower, the guys with the ones which are +1 are these. So of course, if you interchange, you get minus sign. All right. So having actually, and okay, so one thing then that of course, what you can show that that the chi alpha with upper index transforms with matrix M on the right side. Okay? While to remind you, chi alpha was transforming with the matrix M on the right side. Or the left side. Left, right. Okay? So now having those, the important thing that you want that you can do with those spinors, you construct Lorentz invariant objects. Okay? And they're also called, you can have wedge brackets and square brackets, and you obtain them in the following way. That, well, you can just contract indices, yes? So you contract indices, and so we can construct the following object. Well, you can just start with one of them, okay, one spinor, and you contract indices like that. Well, you find that, or what it is up to a sign, is this. But now these spinors here are just numbers. They commute. Okay? So that's important. These are just spinors which are numbers. They commute. Okay? So that it is equal to 0, of course. So you cannot construct a Lorentz invariant spinor product. But you can do the following thing. Suppose they have two of them. Which is very just a result which I call lambda 1, lambda 2. Okay, that will be, you have two different spinors. Now you see that what happens is that the upper index will transform, the left part will transform with inverse matrix. The right will transform with matrix, so they cancel. And this is really Lorentz invariant. So this is Lorentz invariant. Okay, and that object, this again, how I call it this product like that, 1, 2. Okay, and this is like a spinor product of two spinors. Okay, which is a Lorentz invariant, and by the way, obviously it's antisymmetric, yes, because from the property of epsilon symbol. Okay. And then I can do the same thing for the dotted spinors, and the convention is for the dotted spinors, you contract on the left lower index 1 and 2 for dot. And so this is lambda bar 1, lambda 2, and this goes under is okay. And some, again, in one book to be denoted as, there's always people using different type of brackets, but for me, BARD will be with square brackets, okay? And this is, again, antisymmetric. Okay, so we know how to use spinors and how to construct Lorentz invariant objects, okay? And from now on, we think about, it's very important, we think as Lorentz transformation as SL2C. Or this is how we do in the celestial holograph. All right? And these spinor project are like type of a basic elements, basic quantities that use in celestial holography, for example, to express the amplitudes and so on, because, and also this scalicity notation is something which is very commonly now, well, it's like a bread and butter of the amplitudes, program, okay? All right, so, and now, as I promised, now Lorentz transformations will be parameterized, will be represented by these, on spinners, by these 2x2 matrices. So, but we want to get rid, so in other words, we want to get rid of these original Lorentz matrices, these lambda matrices completely. So that's also, we want to replace essentially by these 2x2 matrices. So for example, we have vectors. What we will do them will be represented as by spinners in the following way. We'll introduce a 2x2 matrices. There will be one index which will be dotted, one undotted. And what we do, we simply multiply them by these matrices, which I defined before. And similarly, I will introduce the bar matrix. Like that, all right? And then, of course, you can invent them by using properties of Pauli matrices. It's trivial to see that if you can, have, for example, have this matrix, then the vector can be just, you can read out simply by taking this matrix and trace it with the appropriate, sigma matrix. Okay? So you can go back and forth if you wish. And then what you see that if you have two vectors, let's say V and W, then in this notation, the scalar product is just a trace of the product of these two matrices. Okay? And this is Lorentz invariant because this 2x2 matrices representing vectors transform in the you say bifundamental representation with M on the left-hand side and M dagger on the left-hand side and W bar transform with M dagger -1, invert W, M inverse 1. So of course, if we take a product and a trace, those cancels, and you get Lorentz invariant objects. Okay? Okay. Perfect. Good. So now, okay, we'll go further. Are there any questions at this point? Okay, it's a pretty basic stuff, but it's good to see it, how it, how the whole thing fits together. Okay, I'm sure that many of you have seen that before, possibly many times, but there's still somehow I find that the introductory lectures in quantum field theory, some of them contain that, some of them not. Okay, so it's good to see it. So by the way, if you write it, if you write explicitly these 2x2 matrices, then for a vector, then V will be contained these just combinations of the time component and other components in the following way: I2 and V. 0 minus V3, and if you take a bar, then we'll have essentially Same thing with raised indices. Raised indices, there should be 1, 2, and should be V0 plus V0, that should be minus, right, V3. Okay? So this explicit form of those matrices. And then, of course, when you look at that, you see that determinant of the determinant of V and the same determinant as V bar is nothing else than V squared. Yes? Okay? So it is explicitly, you see now that the determinant of this matrix gives you the invariant length square. Okay? So this is how we think about vectors as a bifundamental representation of SL2C, which transform in this way. All right? Cool. So now we go back. So far, this discussion that I made of spinors and so on and vectors, I didn't make contact back with the Dirac equation because I want to construct something which are called momentum spinors, which are actually solutions of Dirac equations and solutions of Dirac equation, and that again, these momentum spinors will become a crucial ingredient of scattering amplitudes describing fermions and bosons and so on. Essentially, what we will do will, as you will see later, will eliminate everything at the end will be written in the spinor notation. Okay. So now what I have to do, I have to talk about momentum spinors. And then for that, I'll be talking about the Dirac equation with a zero mass. So we talk about the Dirac equation and for massless particles, okay? Because that's what we focus on. Of course, you can do the same thing, and okay, you can look, for example, in this notes, which I have how to do it for massive spinors, but what we want to do here is in the following way, is the for massless case, and then you see that if you write them now with gamma matrices and by representation, so the momentum, so the Dirac equations are like that for upper and lower components. Where, of course, D now is this 2 by 2 matrix. Yes? All right? Of course, that is an exercise to show that from those equations it automatically follows that these spinors satisfy massless Klein-Gordon equation. Okay? That's a trivial exercise. All right. Now, while I'm telling you that proving the Dirac equation is Lorentz invariant involves quite an exercise. It's a homework, and you start at homework quantum field theory. But for us, it becomes completely trivial because now, now I have a transformed spinors, okay, which transform in the following way. And if I go to the boosted frame, or rotated frame, Lorentz transform frame, then Dirac equation is like that, yes? So then, now you see that it is, now I know how D bar transforms under those, under Lorentz transformations. So it is, this D bar transforms, while of course, the spinors by themselves transforms with matrix M, yes? So we see that having a solution of the Dirac equation in one frame, you can automatically produce solution of a Dirac equation in another frame by transforming according to this rule, because this is also equal 0, yes? All right? Okay. So this is, already you see here that it goes somewhere, that this SL2C representation of Lorentz symmetry is simplifies drag equations and many other things. All right? All right, so we want to solve the drag equation, yes? Okay, so let's do it. So we say that, we write it as simple as a plane wave, yes, and of course then we can superpose plane waves. So it is, okay, it solves Klein-Gordon. So some combination of left and right moving waves. Okay, like that. But of course we have two of them. So there's some coefficients here, which I call lambda alpha of p. Okay? And what I want to, and then this is how the solution should look like, because it's a combination of plane waves which satisfy Klein-Gordon equation. All right? And then, of course, this is Klein-Gordon equation, which means that p squared must be equal to 0. Yes? So it's an on-shell condition for the moment. Okay. Cool. Okay. All right. So we want now, so then of course, when you plug it into the drag equation, then this auto satisfies, it's a necessary condition set in Klein-Gordon, but now in momentum space, simply then now these momentum spinors satisfy this equation. Yes? That's the drag equation written for these plane waves. All right? Now to solve it, as I told you, go to the simplest possible frame in which the particle is moving, let's say, in the z direction. Of course, massless particle, yes, p squared equals 0. And then, so the matrix P bar has this simple form, block diagonal form. Okay? And then you can find that then it is trivial, that it must be, okay, that the solution must have a form, must have a 0 upper comma and lower, okay, whatever it is, it's of course a linear equation, so we call it square root of 2 a0, the second component. We start from that. Okay? Or anything multiplied by an arbitrary number, but that's very convenient to choose this. And then, similarly, if you look at the equation for the lambda bar, it looks like that. Okay? All right. So this solves, yes? This is some, you can put here like one jab, for example, if you wish. Okay, it's just a number. Okay? So now, what we do, to find the solution of the drag equation in arbitrary frame, we just transform it, P0 to P, yes, by using Lorentz transformation, well, parameterized now, expressed now as this 2 by 2 matrix M. And then, of course, the equation will be solved for this momentum by the transformed spinor from here. Okay? So this is automatically will be true. All right? So now, actually, there's no need for, we'll write it somehow explicitly in a minute, but at that point, if there's no, just what we know, that the solutions in order to find solution with arbitrary momentum P, yes, what you do, you find the matrix M, yes, which transforms this momentum to another momentum. It is Z momentum. Now, of course, to do it, what you do, you can do the following thing. If you think about it carefully, or what you have to do to transform one light-like momentum into one light momentum, P squared equals 0, you have to rotate 2 times, yes, so that they point, the space-like momentum point in the same direction, and then boost it. So this transformation for momentum P0 to P uses 3 parameters. Uses only 3 parameters. You don't have to use whole Lorentz transformation. And that's very important later. These remaining 3 parameters must leave momentum invariant, yes? And this invariance is something which is called little group invariance, or little Wigner group invariance. Okay, and it will play an important role later. I will explain later. By the way, if you look like that, if you look at these solutions, they have the property that if you take lambda and lambda bar and form just a 2 by 2 matrix in this way, then it will give you this matrix, which I have here, now alpha dot, okay? So it automatically, of course, since everything now you can transform both sides with to a bi-Lorentz frame, then you find that actually the momentum that tells you that any momentum, P alpha dot, can be written as a product of lambda times lambda bar. Okay, now momentum spinors. So a momentum now is written as a product of spinors, dotted and undotted. And as you will see later, this is again something which is basis for the so-called holistic representation of amplitudes. Momenta will disappear by using this relation, and whole scattering amplitudes, scattering amplitudes will be represented in terms of spinor variables. Okay. Now, there's another notation which I want to introduce, which is a very common. But sometimes when you write for lambda alpha, you call it simply like this type of a cat, okay? And for upper one, you call it as this type of a wedge bra, and lambda bar with lower index is like that, okay? And lambda bar with upper index will be, of course, called will be lambda bar for that. Will be like that. Yeah? So that can be written in the nice way. That can be written as this matrix P can be written in the symbolic way like that. Yeah. All right? There's one lambda alpha dot, like that. And then there is another one. Oh, yeah, cool. Okay, so this is the same thing, yes? All right? So now, actually, now you see the following thing. Now we can do it for any momentum. And what you will find is that if you take scalar product, if you take the trace of P times P bar, which we know that was a 2 times P1, P2, then it will be simply, and you see what I will contract this P2. It will be something 1, 2 times 2, 1. And it will be also the same thing as 1, 2, 2, 1. So we see that now the scalar products can be also simply represented in terms of these square and wedge spinor products. All right? So we now, of course, the scattering amplitudes will involve all possible Lorentz invariants, and then what we'll be doing representing by these products, by these products of spinor products. Okay. All right. Okay. So now, so that is so far everything was standard and well known for sure. Now I want to make a connection with, represent those spinors in more celestial way. And this will be done in the following way. I have now this momentum spinor. The momentum spinor is a 2-component complex number, yes? So I can write in the following way. I can write square root of one complex number, which is called lambda, yes? And then this is a 2 complex number. One 2. Yes, I can always write it like that. Okay? And similarly, the dotted spinors, I can draw it as another number, a priori complete different numbers. I call omega lambda tilde, and then some z tilde and 1. Yes? The two component complex vectors. Yes? Then if you write the momentum, then according to this formula which I have here, you have when you multiply a product, omega lambda tilde, and times this z tilde, z1. This is just by using this definition. All right? All right. Which means that if you write, so now if you go back to what it means in terms of 4-component spinors to make 4-component vectors, yes, 4 vectors, then you see that P0, P1, P2, P3 is square root omega lambda bar by 2, and then you have a 1 plus z tilde. Okay, this minus, okay, z tilde, if I didn't make a mistake with signs, these signs change from, one set of nodes to another nodes, yes? And then you have 1 minus z tilde. Okay? So this is how momentum looks if you represent momentum spinor in this way. By using this product relation, you see now the momentum is parameterized in this way. All right? Okay, so this is very good because, this is for any momentum. Now, however, momenta are real. Yes? So momenta are real for us at this point. Later we'll consider complexified momenta, which means that this product must be real. Let's call it lambda, or let's call it omega. Yes? And then, of course, if again real momentum P, so this must be real. And then for real momentum P. Okay? And then in addition, if this is to be real, the momentum has to be real, then of course it's easy to see that z tilde should be equal to complex conjugate of z, yes? For real momenta. Okay? That's very important. And now we can look back, look at this representation. This is something, and I will see why, these complex, so now we have actually each momentum is characterized by omega 1, which would be some energy in some frame, and plus 1 complex variable z, which is essentially parameterized direction of the momentum, yes? All right? And now we can look what Lorentz transformation do to it. And the Lorentz transformation, so we take omega, okay, so this is, and we rotate it by matrix. Now let's represent this 2 by matrix in the following way. This is in matrix M. So it will transform into that. Yes? Yes? So matrix multiplication, which means that now, comparing with the original expression, which was a Z1, you see that what is happening, that, you factor out the CZ plus D, so you can write it now, summarize the transformation, that omega transforms times omega times CZ plus D squared, while Z then will transform AZ plus B by CZ plus D, with a matrix, this is a matrix M, which is determinant, which has determinant 1. Okay? All right? So that is very important. By the way, this transformations is something which is usually, if you took a course in complex analysis, it's called Mobius transformations of a plane, which are isometries of a sphere. And so essentially, when you think about z coordinates, the z-plane, and then think about the sphere, which is equivalent with from stereographic projection. Then you see, for example, if you look now, for example, if you take, for example, the boost in the z direction, then z obviously transforms, is simply rescaled. Yes? All right? Which means that it is rescaled, so boosts in the z direction, send plane away from, further away from the origin, which means they send them, and send them more towards the North Pole. Okay, so now we see now, if you look at the advertisement of Sabrina Stock, you will see that actually, now we think about the sphere as a celestial sphere, okay? And you are moving towards north direction, yes? Which is generated by this boost. Then the stars will pile up in front of you, yes? They move towards the North Pole. So that explains this picture, and that explains connection to celestial sphere. We will later think about the z-coordinates and z-coordinates on celestial sphere, okay? And then, okay, almost done. But in general, you have all these, the Lorentz transformation with 6 parameters are now encoded in this, 6 parameters, because you have here additional constraint determined is equal 1, yes? All right? So boost corresponds to rescalings, dilations, okay, or rescalings on the complex plane of Z. Now just to write down just a couple of equations which are left out, which I wanted to, so that you see, and which we'll be using later. Then, for example, if you write like this scalar product and then this parameterization, that will be simply omega lambda 1, omega 2 lambda. And now you see that this is with epsilon, since both of them have this form. Okay, then it will be like a cross product, yes, sort of. So it will be Z1 minus Z2, and that will be equal to, so that object is usually called Z12. Okay? And then same thing if you do for the square brackets. Okay, lambda, I should put a lambda here. And then times Z12 star. So the product, scalar product, which is 2p1, p2, is going to be nicely written. Now you have this these two products will add up to these energies, omega 1, omega 2, times Z12 square. Okay, so in other words, now we can do two things. I told you the first step was we can do an amplitude, and as you will see, an Lorentz invariant object, right, in terms of this Helly's spinors and a function, Lorentz invariant function of momenta, and then instead of those spinors, we can use this representation, and then this makes a connection with the coordinates on the, we will be using these z coordinates, which are complex coordinates, which we later identified in the spirit of this, something which is called celestial map, with positions of points on the celestial sphere. All right. All right, good. Any questions? You don't need to clap. It's good. All right. Yeah.
We have some like conjugation with the bars floating around when we
Yeah.
get to complex momenta.
Yeah, I will talk about it later. I will answer. You will see that for real momenta, they are not exactly. You see the point here. They are not exactly even for real momenta. Lambda and lambda bar not exactly complex conjugate to each other, because there's this. You can make them complex conjugate by appropriate transformation with this remaining little group Lorentz transformation. Okay, but as it is now, lambda is and lambda bar are, I give you explicit representation, only the only thing, yeah, like that, yeah.
Will we discuss the connection to conformal field theory?
Well, that's next.
Okay.
And this lambda bar, it carries dotted index or not?
Which one?
Lambda bar.
Lambda bar, yeah, in my notation. Okay, lambda bar has a dotted index, and now it can be lowered or uppered. The relation to Dirac is that this up alpha dot at the right is upper dotted, while the left-handed, the top two, are lower undotted. Okay?
If you, instead of using massless spinners, use
Yeah.
the massive ones in this construction, does it change much?
If you do what?
If you, instead of using massless spinners,
Yeah.
you use the massive ones, doesn't the construction change much?
No, you can, that's actually very well, it's described in detail in this one of the scores, to which you have a link on the website. You can really, then actually what happens is the Dirac equation couples left to right. Yes? Well, the advantage of zero mass case is that you have a separate left and right independent, so that's why actually you have, that's why we can have just left-handed well, in the standard model, old standard model, we have the left-handed neutrinos, and we do not have right-handed neutrinos, yes? You have left-handed neutrinos, right-handed neutrinos. Yeah, all right. Oh, there's a spider here. Yeah, okay, well, let's leave it at peace. It's a bad luck if you do anything to it, yes? Okay, yeah. Anything? Okay, and you see here already this transformations which I wrote, they make a connection. This is exact transformation with CFT. So the next, now we take a break, yes? Okay, and then we're up to 11? Until we have a break until 11, okay.